Science isn't just reading books, it's about doing. Today we're going to put our knowledge of Newton's laws into action by learning how to properly plan and conduct scientific investigations. We need to move from just knowing that force causes acceleration to actually proving it with data. Learning to design a good experiment is the most important skill in science. Every strong investigation begins with a crystal clear scientific question. This question can't be vague. It must be testable and measurable. For example, a good question might be, if I increase the mass of a cart, how will that affect the distance it rolls on a flat floor? This question directs your entire experiment and focuses your data collection. Once you have your question, the next step is to identify your variables. The independent variable, IV, is the factor you choose to change, like ramp height or amount of force. The dependent variable, dV, is what you measure in response, like the speed or distance traveled. All the other factors, like the temperature or the type of surface, are controlled variables, CV, that you keep exactly the same. Let's use an example. Does the mass of a toy car affect the distance it travels off a ramp? The independent variable is the car's mass, which you'll change by adding weights. The dependent variable is the measurable result, the distance the car travels from the ramp's edge. And the controlled variables must stay the same, such as the material of the car, the height of the ramp, and where you start the car. Before you start, you must make a prediction called a hypothesis. This isn't a wild guess. It should be an educated guess based on science principles, like Newton's second law. You can frame it as an if, then, because statement. For our car experiment, you might say, if I increase the car's mass, then the distance it travels will decrease, because greater mass requires more force to accelerate, as Newton's second law states. The procedure is the step-by-step plan that makes your investigation a success. It must be so detailed that any person, using only your instructions, could set up the experiment and get similar results. A good procedure eliminates confusion and ensures you test only what you intended to test. The procedure starts with listing the materials and setup. You should list your tools like the ruler and stopwatch and draw a simple diagram. Make sure to clearly mark your start and finish lines. If you're using scales or rulers, ensure they are set to 0 before starting. A solid setup is half the battle won. When writing the step-by-step instructions, be very specific about how you change the independent variable. Instead of saying, change the mass, say, add 50 grams of mass to the car, securing it with tape. Then, detail exactly how the dependent variable is measured. Measure the distance from the end of the ramp to the front bumper of the car, recording the distance in centimeters. The single most important part of the procedure is controlling variables. If you fail to control your variables, your conclusion will be invalid. If you change the mass, but also accidentally push the car a little harder each time, you won't know if the distance changed because of the mass or the extra push. Your procedure must be strict about keeping every factor constant except the one you're testing. Once you start collecting data, never trust a single result. You must conduct multiple trials for each change you make to the independent variable. 3 trials is a good minimum. Running multiple trials helps you spot errors and ensures that a weird one-off result doesn't throw off your whole experiment. You'll use the average of these trials as your final, most reliable data point. As you collect data, organize it right away in a data table. This table should have a column for your independent variable, separate columns for each trial's results, and a final column for the average result. Make sure to label your column headings with the correct units every single time, whether it's grams, seconds, or centimeters. After collecting your trial data, calculate the average for each change you made. For example, if your 3 distance trials for the 50-gram mass were 10 centimeters, 12 centimeters, and 11 centimeters, you add them. 10 plus 12 plus 11 equals 33 centimeters. Then you divide by the number of trials, 3. 33 divided by 3 equals 11 centimeters. The average of 11 centimeters is the most reliable result. Once the data is collected and averaged, it's time to visualize it with a graph. Graphs reveal patterns immediately. Remember the rule for axes. The independent variable goes on the horizontal x-axis. That's the factor you controlled. The dependent variable goes on the vertical y-axis. That's the factor you measured. Now we analyze the results by looking at the graph's trend. If both your variables increase together, you have a direct relationship, like the one between force and acceleration. If one variable goes up while the other goes down, that's an inverse relationship, like the one between mass and acceleration. Finding these relationships proves a scientific law. When analyzing, also look for outliers, data points that seem way off from the main trend. These often indicate an error. Perhaps you misread the ruler, or the car ran over a pebble on one trial. If an outlier severely messes up your average, you should investigate what went wrong and maybe repeat that trial if time allows. The final step is the conclusion, where you tie everything together. It must answer the original question and state whether your initial hypothesis was supported or rejected. Crucially, the conclusion isn't complete until you provide specific evidence, your average data values, to back up your claim. For the car and mass experiment, a strong conclusion would be, my hypothesis was supported. Then, for evidence, as shown by the data, when the mass increased from 50 grams to 100 grams, the average distance traveled decreased from 25 centimeters to 15 centimeters. Finally, you explain the why, linking it to Newton's second law. Greater mass creates greater inertia, resisting the initial force. A good scientist always questions their own work. The evaluation part of the conclusion forces you to think critically about the quality of the experiment. Did you use the right materials? Were your controlled variables really controlled? Did the friction change over time? Evaluating your procedure is key to understanding the limitations of your findings. Based on your evaluation, you should suggest improvements. For instance, if you used a stopwatch and noticed inconsistent timing, you might suggest, next time, we should use a motion sensor to measure speed electronically, which would be more precise than using a human-operated stopwatch. This shows you've thought scientifically about improving the reliability of the data. Remember that science is a continuous process, a cycle. You start with a question, you hypothesize, you test, you analyze, you conclude, and then you use that knowledge to improve your investigation or ask a new question. Planning and conducting investigations is how you take motion and forces from textbook concepts to real observable science.